Ba-da-ba-ba-ba. I'm loving it.
All right, this is CS50. This is week 2, wherein we will ultimately learn how to use memory. But we'd first begin with a bit of story time. And in fact, allow me to walk over to our brave volunteers who have joined us already. First, here on my left, we have who?
Hi.
Okay. Do-do-do-do.
I'm Akshaya. I'm a first year in Matthews, and I'm planning on concentrating in chemical and physical biology. Biology and CS.
Wonderful, welcome. And let me have you hang on to the microphone first, because we've asked Akshaya to tell us a short story. So in your envelope, you have the beginnings of a story. If you wouldn't mind reading it aloud. And as she reads this, allow us to give us some thought as to what level Akshaya reads at, so to speak.
All right, it's a long one. Get ready. One fish, two fish, red fish, blue fish.
All right, very well done. What grade level would you say she reads at? If you think back to your middle school, grade school, when maybe teachers said you read at this level or this one here. It's okay, no offense taken yet.
Okay, so I am getting that seeing videos, typing, and streaming at the same time is not going to be ideal. Okay. Probably not ideal. Let's delete things we don't need. Close groups. Mount some.
is just about right. And in fact, according to one algorithm, this text here, one fish, two fish, red fish, blue fish, would indeed be considered to actually be first grade or just before first grade. So and why is that though? Why did you say first grade? It's very basic, but what is it about these words that are very basic? Do you want to identify yourself?
Sure, they're all one syllable and they're very simple, like colors and stuff like that.
Spot on. So like they're very short words, they're very short sentences, and you would expect that sort of a younger person. All right, let's go ahead and hand the mic to your next volunteer here. Let's introduce yourself.
Yes, hi, I'm Ethan. I'm a first year in Canada, and I will be concentrating in economics.
Wonderful. And in your folder, we have another story to share.
Congratulations. Today is your day. You're off to great places. You're off and away.
So this text might sound familiar, particularly on the heels of high school, perhaps. What grade level might he be reading at? So maybe 5th grade, and why 5th grade? Okay. Yeah, so a little more complicated, like the words, we've got some more punctuation, we have an apostrophe, we have longer sentences, and indeed, according to one algorithm, not quite 5th grade, but we would adjudicate your reading level to be 3rd. But let's see if we can't do one final flourish here, if you'd like to introduce yourself and your story.
Hi, I'm Mike. I'm also a first year. I'm in Weld, and I'm planning on concentrating in biomedical engineering.
Welcome. And your tale.
It was a bright, cold day in April, and the clocks were striking 13. Winston Smith, his chin nuzzled into his breast in an effort to escape the vile wind, slipped quickly through the glass doors of Victory Mansions, though not quickly enough to prevent a swirl of gritty dust from entering along with him.
All right, so escalated quickly, and someone's guess at this reading level? Okay, 1984 is indeed the text in question, and in what grade did you perhaps read that book? So I'm hearing 8th, I'm hearing 10th. So indeed, 10th grade is what a certain algorithm would actually adjudicate that reading level to be at. And consider now the heuristic. So we started with very small words, very small sentences, very easy words, and then things sort of escalated into more interesting, more sophisticated English, more interesting sentence construction and the like. So I bet if we could somehow capture those characteristics of text, the length of the words and the lengths of the sentences and the position of the punctuation, I dare say even using week 1 material and today week 2 material, we'll be able to actually write code and implement an algorithm like that can take these spoken words, put them to paper, and actually analyze roughly what that reading level might be. So that's just a teaser of what lies ahead. For now, allow us to thank our volunteers, each of whom gets a wonderful parting gift here to read at home. All right, and thank you all so much. So with that said, there's another domain that we'll explore this week, and indeed what you'll find in the coming weeks is that beyond just focusing on some of the fundamentals and the basics, like we've really done the past couple of weeks, talking about loops and conditionals and Boolean expressions, really building blocks or puzzle pieces that we can assemble together, we're going to increasingly start talking about applications of these ideas, which after all is why any field is perhaps important and applicable. So here, for instance, we'll consider not only reading levels today, and in turn in problem set 2 this week, but also the world of cryptography, which is the arts, the science of scrambling, encrypting information, and ciphering it in such a way that you can send a message securely through the internet, through the air, through any medium, even though someone might intercept it. Ideally, thanks to cryptography, they shouldn't be able to decrypt it or actually determine what it there says. So for instance, if you were to receive a message like this, at first glance, it's indeed a bit cryptic, 3 words maybe, but by today's end, we'll have decrypted even this message for you. So up until now, though, we've had some sort of conceptual training wheels on, and I gave us this picture last week when we introduced the tool Make, via which you can make programs out of your source code, because you need to turn that source code into machine code, the zeros and ones. And in the middle here was this thing called a compiler. But it really has been kind of an abstraction for us, and we've sort of had these metaphorical and sort of physical training wheels here in the sense that we haven't really needed to care like what the compiler is doing, how it works, and so forth. But today, what we thought we'd do is peel back a bit of that layer so that even though after today you'll continue to be able to use commands like make and sort of return to the beautiful abstraction that is not caring about some of these lower level details, we'll offer you a glimpse of how some of these things work, because so that inevitably when something goes wrong, you've got some bug, you're having some problem, you'll have a bottom-up understanding of what it could actually be. And indeed, these basics you'll find will very often help you troubleshoot problems and really solve problems more generally. So here, for instance, is the code that we keep coming back to. And this code here is the simplest of C programs that just says hello world. This is the source code. This we claimed was the corresponding machine code. And it was that program called a compiler that converted one into the other. But let's dive a little more deeply this week into what we mean by compiling code. Like, what is happening so that by day's end, nothing really feels like magic anymore. It's not just that it goes from source code to machine code and that's that. You understand like what's actually being done for you, and frankly, what other humans have done over the decades to make as beautifully abstract and as simple as it now might seem to be. So here are the couple of commands that you've been in the habit of running when you want to first compile your code and then execute your code. But it turns out that make is actually running another command for you. The first of several white lies we'll tell in the course is that make itself is not a compiler per se. It's actually a program that automatically runs a compiler for you. And by that, I mean this. Let me go over to VS Code here, and let me create our familiar hello.c program. And I'm going to go ahead and do include standard io.h, int main void, and inside of the curly braces printf hello, comma, world, \n, semicolon. So that's the code that we keep writing again and again. And up until now, if I wanted to compile that, I would do make hello, /hello, and voila. Now my program is made and it actually executes. But what's actually going on underneath the hood there is that make is running an actual compiler for you. And the reveal today is that the compiler we have been using is something called Clang for C language. And this is just another program whose purpose in life is actually to do the conversion of source code to machine code. But it turns out that Clang by itself can be used very simply, like you see here, Clang hello.c, but it doesn't behave nearly as user-friendly as you might like. So in particular, let me go ahead and do this. I'm going to go ahead and remove my compiled program by running rm for remove, which I alluded to briefly last time. And then I'm going to say y for yes, remove that regular file. And if I go ahead now and run just Clang of hello.c and hit enter, it seems to be successful, at least insofar as there's no error messages. But if I try to do /hello enter, there is no such file or directory called hello. That is because by default, Clang somewhat goofily like just outputs a file name called a.out. Like why a? Well, it's sort of a simple name, a.out, technically for assembler output, but this just means this is the default file name that Clang's going to give us. So, okay, it turns out I can do /a.out enter, and voila, now it's my program. It's just kind of a stupid name for a program, right? It's not very user-friendly. It's certainly not an icon you would want to put on people's desktops or phones. So how can we do better? Well, it turns out with Clang, we can configure it using what we'll call command line arguments. And command line arguments are actually something we've been using thus far. We just didn't slap this word on it. But command line arguments are additional words or sort of shorthand notation that you typed at your command prompt that somehow modify the behavior of a program. And you can perhaps guess where this is going. It turns out that if I actually want to create a program called hello, not a.out, which is the default, I can actually do this. Clang space -lowercase o space hello, or whatever I want to call the thing, space hello.c. And now if I hit enter, nothing seems to happen. But now if I do /hello and enter, now I've actually got that program. So why is make useful? Well, it just saves us the trouble of having to type out this longer line of command anytime we actually want to compile the code. But in fact, it gets even worse than that with commands like Clang or compilers in general, because consider this code here, not just the version of Hello World, but maybe the second version wherein last week I started to get user input by adding the CS50 library, using getString, and then saying hello, comma.
סבבה, איתך?
David. Well, if I go back to VS Code and I modify this program to be that same one, so let me go ahead and include CS50.h at the top. Let me get rid of this simple print line and instead give myself a string called name equals get underscore string. What's your name? Question mark, just like we did in Scratch. Then I can do printf, quote unquote, hello, comma, and previously I typed world. I obviously don't want to type David because I want it to be dynamic. What did I type last week for as a placeholder? So yeah, just not command S, but %S. So %S in this case, which is a placeholder for any such string. Then I can still do my new line, close quote, comma, and then I can substitute in something like the value of the name variable. All right, so if I go ahead now and compile this, now last week I could just do make hello and I'm on my way. It worked just fine. But if I instead do clang manually, it turns out that this is not going to be sufficient now. Clang -o hello space hello.c. Exact same thing I typed a moment ago, but I think I'm going to see some errors. So what's this error hinting at here? Well, at the very bottom, it's a bit arcane with its output, and much of this you can ignore, but there are some certain keywords. What's the first maybe keyword you recognize in these 3 lines of erroneous output? So it mentions main. That's not that much of a clue because that's the only thing I wrote so far. Second line, though, get string. If there's some issue with an undefined reference to get string. Now, why might that be? I did include CS50.h, but that's apparently not enough to teach the compiler about getString. Well, it turns out that if you're using a third-party library, one that doesn't necessarily come with C as a language, something like CS50s, it turns out that you additionally have to tell the compiler that you want to use that library, and not just by including the header file, but by an additional command as well. So when you run Clang, you want to provide an additional, rather, command line argument, literally -L for library, which is a term I used last week, CS50. A library is just code that someone else wrote that you want to use in your project. So if I really want to compile this version that uses the CS50 library, I can still do clang-o hello, hello.c, but before I finish my thought, I need to tell the compiler to link, so to speak, in the library CS50. And now I hit enter, the error message goes away, I can do /hello, I can type in my name, and voila, we're back to week one. And this is why, suffice it to say, we introduced Make, which is not a CS50 thing. This is a popular tool that the real people in the real world use to automate these kinds of processes. So unbeknownst to you, Make has been using the -O for you. Make, unbeknownst to you, has been using -L CS50 for you, just because it makes our lives easier. But today, we thought we would deliberately sort of peel back this layer so we at least understand what's going on behind this abstraction that is Make itself and compiling more generally. So let me propose that compiling itself is not quite what we've described it to be. Compiling is like this catch-all phrase that apparently I claim goes from source code to machine code. But if you really want to get pedantic, which we'll do briefly, but this is not a sign of things to come because this too will be abstract away, compiling is just one of 4 steps that are involved in turning source code that you and I write into those zeros and ones. But through an understanding of these 4 steps today, you'll hopefully better understand how to troubleshoot issues like that and just kind of know what's happening, because it's not in fact magic. It's just the result of years of humans developing these 4 steps here. So when you run Make, what's happening, or in turn, when you run Clang, 4 different things are happening. And the first one is called pre-processing. So what is this all about? Well, let's consider this code here. And this code's a little bit interesting insofar as it's one of the more complicated examples from last week. And you'll notice, for instance, that I had include standard IO at the top, so I could use printf. I had main down here, whose purpose in life was just to meow 3 times. And then recall we made our own meow function, just like we did in week 0 with Scratch, that just printed out quote unquote meow. But I also included this line here, which we called what? This was a prototype, and why did I have to include it there? Or equivalently, what would happen if I didn't include a prototype up at the top there? Exactly. If I didn't include it up here, the program, when trying to compile main, would not know what meow is because it's not defined until later. So this is kind of like a little hint of what is to come. Alternatively, we could just move this whole thing up at the top of the file, but I claim that that just devolves into a big mess eventually once you have many different functions.
Yeah.
Like you can't realistically put them all at the top to solve this problem. So these prototypes solve that problem. So nothing new here, just a reminder of what motivated this one line of prototype.
Okay.
Now let's consider this simpler program, which is just the one we wrote most recently in VS Code. This program prompts the human for their name and then says hello to that person. But it has 2 includes at the top of the file. And in fact, any line of C that starts with this hash symbol is what we'll call now a preprocessor directive. It's not really a word you need to remember in your vocabulary, but it is a little bit different from most every other line because it starts with that hash. That's sort of a special symbol in C. And what this means is the following. This very first line, CS50.h, is indeed a file that I and CS50 staff wrote, and we installed somewhere in VS Code for you, somewhere in the cloud. And I've claimed you need to use this header file in order to use getString. So just logically, what is probably inside of CS50.h? Yeah.
Prototypes.
Super close. So the function called getString that does the getting of a string, but it's not quite as much as the function itself. It's actually a little bit less than that, but you're on the right track. What is inside of CS50.h? Presumably, just a what? Just a prototype for which function? GetString. So admittedly, there's some other stuff in there too, but the important line for today's discussion is that inside of CS50.h is indeed one line of code that defines what the return value, what the name is, and what the arguments, if any, are to getString, and some other stuff. And so what happens effectively when you compile your code, step one is this pre-processing line. And essentially, there is some code that someone else wrote inside of the Clang compiler that looks for a line that starts with #include. And when it sees that, it goes and finds this file and effectively copies and pastes the contents of that file right there into your code so that you don't have to go find the file, copy and paste it, and make a mess of your own code. Yeah. So in particular, it's effectively as though you're copying and pasting the prototype of getString to the very top of your file, thereby teaching the compiler that it exists. By that same logic, what is probably in standard IO.h? The prototype for printf, and indeed, exactly that. So this line effectively gets replaced with the equivalent of the prototype for printf, which for today's purposes is a bit more complicated. So let me wave my hand at the ... just because it takes a variable number of arguments depending on how many placeholders or format codes you have. But effectively, that too is what's happening. So the preprocessor step 1 of 4, just does that find and replace, if you will. Now there's some other stuff in that file, and this too is kind of a white lie. Printf probably has its own file because that's a really big library, but the essence of it is exactly this. So preprocessing converts all of those #include lines to whatever the underlying prototypes are within the file, plus some other stuff. Now compiling, we use it as this catch-all phrase, but it turns out it has a very specific meaning that's worth knowing about, even though after today you can go back to using compiling as the sort of catch-all phrase. So when you've got this same code here, after the pre-processing step has happened, so this is essentially happening in the computer's memory. It's not changing your hello.c file permanently or anything like that. This code gets quote-unquote compiled into something that looks more like this. And this is a scarier language that we won't spend time on in this particular class. This is what's known as assembly language. And back in the day, before there was C, humans wrote this to program their computers. Yeah. Similarly, before there was assembly code back in the day, humans very initially used what instead? So zeros and ones, like they actually wrote the machine code painfully, be it in code or be it in punch cards, like physical objects or the like. So again, these are sort of abstractions, but we're rewinding for today in time. But what this compiler for C is doing is converting C into this other language called assembly language. And even though this looks very esoteric, there's at least some juicy things in here. If I highlight getString is mentioned in this code, printf is mentioned in this code, and even some of these keywords here that are spelled a bit weirdly, this relates to subtracting and moving something in memory and calling a function. So there's some semantics that are probably somewhat familiar, even though this is not code we ourselves will write. But unfortunately, this is not yet machine code, and that's where step 3 comes in. So step 3 of this 4-step process is technically called assembling. And assembling just takes that assembly code and converts it, thankfully, to the thing we do care about, the zeros and ones. So assembling takes assembly code, converts it to zeros and ones. As an aside, and I alluded to this earlier, the reason that Clang names its files a.out by default, assembler output, is kind of a side effect of that being one of the steps in this process. Okay. Assembly language and its subsequent output. All right, so here are some zeros and ones, but unfortunately, there's still that 4th and final step, which is a word that I also used earlier, namely linking. So let me take a step back and look at this code here. And even though this code is exactly as I wrote in VS Code in hello.c, so no copying and pasting, no prototypes have been plugged in here, this is my code, technically there's 3 different files involved in compiling even something relatively simple like this. There's obviously this thing itself, hello.c, which I wrote. There's apparently CS50.h, and there's apparently standardio.h. But technically, and you don't have to know this file name per se, somewhere else on the computer's hard drive, so to speak, is a CS50.c file, which actually contains the staff's implementation of getString and getInt and getFloat and all of those other functions. Somewhere on the server's hard drive is standardio.c that implements printf and all of these other functions as well. So the .c is just inferred from the .h here. You don't ever mention the .c file, but someone else wrote those files, someone else stored them in the server for you, CS50 staff in this case. So technically, even when compiling a relatively short program like this, you're really combining 3 files, at least at the end of the day. And I'll write them from left to right. Hello.c, which I wrote, with CS50.c, which the staff wrote, and then standardio.c as well. So somewhere there's these 3 files, and Clang, our compiler, needs to compile each of these into the corresponding zeros and ones. Lastly, this is not yet sufficient because these zeros and ones haven't been linked together. I mean, I deliberately left a gap here to imply that these are 3 separately compiled files. So that 4th and final step, called linking, takes all of these zeros and ones and in an intelligent way combines them into just one final file named hello, named a.out, whatever the file name is of choice. So what you and I, for the past week, have just been calling compiling, and that's what a typical normal person will use henceforth to describe this whole process. Technically, there's these 4 different steps underneath the hood, each of which is sort of a representative of an evolution of technology over the years. And nowadays, if we fast forward a few weeks in class, when we start talking on, which is another more, is going to be conceptually even higher level, even though underneath the hood, there's going to be some lower level principles at work.
Okay.
So any questions on just terminology or these processes known as compiling? Yeah. Sure, compiling, if I rewind, is the process of taking your source code, which looks like this, this, and converting it into assembly code. So pre-processing just converts all of those hash include lines and a few others to their equivalents. So that's step 1. Compiling converts the C code into the underlying assembly code. The assembling step, step 3, converts the assembly code to zeros and ones. And then the 4th step, linking, combines all of the zeros and ones from the 1, the 2, the 3 or more files that are involved in your project and links them all together for you magically. But at the end of the day, all of this is sort of happening automatically for you. If I jump now to the end here, whereby just by running make, which in turn runs Clang for you, like all of this is abstracted away. But the key here is that even with these commands that we've been running, be it the make command or the Clang command, everything should be explainable what you are typing at the prompt ultimately. Each of those things has a purpose. So any questions then on what we've just now called compiling, even though it's only when you take another CS course that you might spend more time on assembly language or these lower level details. Yeah. A good question. Are there other types of compilers? Yes, back when I took CS50, I used a popular compiler called GCC, the GNU Compiler Collection, which still exists actually in the code space that you're using for CS50. Clang is somewhat more recent. It's gaining popularity, and frankly, we use it in large part because its error messages are slightly more user-friendly. You might not believe us, because if you encountered some errors with your code this past week, they were probably just as arcane as the error message I saw, but it's better than it was some years ago. And there's alternatives to compiling too, but more on that when we get to Python as well. Other questions? All right, well, what are the implications of the fact that we're going from source code to machine code? Well, it stands to reason that if you can compile code, maybe you can decompile it. That is, go in the reverse direction. Go from zeros and ones to actual source code. Now, that would be handy if you want to go in as a programmer and like change something in a program that you or someone else already wrote. It's maybe not ideal for your intellectual property, though, if you are the person who wrote that program in the first place. If you are Microsoft and you wrote Microsoft Word or Excel that people with Macs and PCs and phones have installed on their devices, you know, it doesn't actually sound very appealing if any old customer can take those zeros and ones and reverse engineer them, so to speak, into the original source code, because then they can have their own version of Microsoft Word and make changes to it without really having put in all of the R&D that it might have taken to build the first version thereof. But it turns out that reverse engineering, so sort of doing things in the opposite direction, is easier said than done, because there are multiple ways, as you've seen already, to implement programs, like loops alone. You can use for loops, while loops, even do while loops. And so there's other ways, there's multiple ways to solve the same problem. So even if you try to reverse engineer a program and convert machine code back to source code, there's not necessarily going to be an obvious way to do so. And the reality is that it ends up being such a mess because you lose the variable names typically, you lose the function names typically, that what you end up looking at might very well be C code, but it's completely difficult for you, even a good programmer, to read. And generally the sort of mindset is, if you're really good enough to decompile code in that way and read it subsequently, even without good variable names, good function names, good documentation and the like, you could probably have just implemented the program in the first place yourself without jumping through those hoops. So there's sort of some practicality pushing back on what are otherwise potential threats to, say, your intellectual property. But that's not going to be the case later on in the term when we do get to languages like Python, to some extent, other languages like JavaScript. Some of those are actually going to be readable by anyone, any of your customers, any of your friends, any of your family that actually use.
Okay. Ooh. Oh, I'm so tired. Oh, 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 oh. Okay.
Your program. So with that said, let's introduce now another tool to our toolkit that will hopefully make some of the pain from this past week when you did encounter bugs a little more manageable. And indeed, part of the process of writing code to this day is debugging it. And it is a rare thing to write a program, be it in C or any other language, and get it 100% right the first time. I mean, to this day, I still, 20 plus years later, still write buggy code, hopefully a little bit less of it. But anytime you're adding a new feature, anytime you're doing something for the first time, you're not necessarily going to see all of the possible mistakes. So even in industry, bugs are omnipresent, which is really to say having techniques to debug code, that is, eliminate bugs, is super compelling. Now, just for a bit of history, here is Admiral Grace Hopper, who was actually in not only the military, but also on the faculty of Harvard years ago, and worked on a Harvard computer called the Harvard Mark I, which is actually on display at the School of Engineering and Applied Sciences, if you take a tour over there sometime. But also when working on the Harvard Mark II, she is known for having at least popularized the phrase bug to mean a mistake in a computer's program, in a mistake in a computer's code. And the etymology of this supposedly is this here logbook, wherein she and her colleagues were sort of documenting processes being computed on computers, that a moth actually got stuck in one of the relays, one of the mechanical, the electric relays inside of the very old now computer. And someone very cleverly wrote, first actual case of bug being found. So it wasn't she who actually discovered it, but this was a story she was thereafter fond of telling as a famed computer scientist thereafter. We now know bugs to be all too familiar when it comes to writing our own code, and I thought I would deliberately write some buggy code based on some of the programs with which we experimented last week. So let me go back over to VS Code here, and let me propose that I do something somewhat simplistic, just like this, to print out a column of bricks of height 3. So I'm going into VS Code, and I'm going to deliberately call this program buggy.c, because I intend to do this poorly. I'm going to include standard.io.h as before, int main void as before, and in here, if I want to print a pyramid of height 3, I'm going to do for int I gets, all right, I'm still new to programming in my mind here, so like I know I'm supposed to start counting at 0, okay, and I want to do this until I count up to 3, so I'm going to do that, and then I++, I remember from class in this way, and now I might go ahead and print out just a hash mark, \n, which I do want, because I want to move this cursor to the next line to make this vertical. But of course, if you've noticed with your eye already, when I do make buggy, it compiles okay. So no typos, no syntactical errors. But when I run this, I'm going to see how many bricks. So 4 in this case. Now, this is meant to be a simplistic example so that we don't spend time trying to figure out what the bug is, but rather focus on techniques for actually identifying the bug. So, finding rather the bug. So what's one of the first tools in your toolkit? Literally one you have already. Printf is your friend. And it is a very quick and dirty tool for just seeing what's going on inside of the computer when you don't have more sophisticated tools or even the time to use them.
Okay.
And so in this case, for instance, what I'd propose is that, all right, I'm obviously seeing 4 hashes, and let me play a little slow here. It'd be helpful for me to understand why, logically, I'm ending up with 4, even though I'm starting at 0, like I remember from class, and I'm going up to 3, as we did in class, like I'm just not seeing it in this particular story. So what I would commonly do is go into my code and just help me see what's going on. And I might literally write a printf line like, I is %I \n, comma, and then just print out the value of I. I just want to see on every iteration, what is I, what is I, what is I, just to help me see what the computer already knows. So let me go ahead and recompile buggy. Let me rerun buggy, and then let me make my terminal window bigger just to make clear what's going on. And now it's a little more pedantic. Now, I is 0, I get a hash. I is 1, I get a hash. I is 2, I get a hash. Wait a minute, I is 3, I get a hash. So clearly now it should be maybe more obvious to you, especially if the syntax itself is unfamiliar. I certainly don't want this last one printing, or maybe equivalently, I don't want the first one printing. So I can fix this in a couple of ways, but the solution, the most canonical solution, is probably to do what with my code? To change what to what? Yeah.
Like Less than.
Yeah, so change the less than or equal sign to just a less than sign. So even though this is like counting from 0 to 3 instead of 1 through 3, it's the more typical programmatic way to write code like this. And now, of course, if I do make buggy, and I'll increase my terminal window again, /buggy, now I see what's going on inside of the code. Now it matches my expectations, and so now the bug is gone. Now, of course, if I'm submitting this or shipping it, I should delete the temporary printf. And let me disclaim that using printf in this way, just to help you see what's going on, is generally a good thing. But generally adding a printf and a printf and a printf and a printf, like it starts to devolve into just trial and error, and like you have no idea what's going on, so you're just printing out everything. Let me propose that if you ever find yourself slipping down that hill into just trying this, you need a better tool, not just doing printf. And frankly, it's annoying to use printf because every time you add a printf, you have to recompile the code, rerun the code. It's just adding to the number of steps. So let me propose instead that we do this. I'm going to go back into VS Code here, and I'm going to write a different program that actually has a helper function, so to speak, a second function whose purpose in life is maybe just to print that column for me. So I'm going to say this, void print column, so I could call it anything I want, and this function is going to take a argument or a parameter called height, which will tell it how many bricks to print, how many vertical bricks. I'm going to do the same kind of logic for int I equals 0, I is less than, I'm going to make the same mistake again, less than or equal to height, I plus plus, and then inside of this for loop, let me go ahead and print out the hash mark. So I've made the same mistake, but I've made it in the context now of a helper function, only because in main, what I'd like to do now, just to be a little more sophisticated, is get int from the user for the height. And when I do get that int, I want to store it in a variable called n, but I do need to give that variable a type, like last week, so I'll say that it's an integer. And now, lastly, I can print underscore column, passing in, actually I'll call it h just because height is h, print column h, semicolon. Okay, so it's the exact same program, except I'm getting user input now, so it's not just going to be 3, it's going to be a variable height, but I've done something stupid. I've done 2 stupid things. So this, of course, is not supposed to be there, so I'll fix that. And someone else, what else have I done? Yeah, I'm missing the prototype. And this is, let me reiterate, probably the only time where copy-paste is okay. Once you've implemented the function, you can copy-paste its first line, add a semicolon, so that it teaches the compiler that this function will exist. 3 stupid things. Okay, thank you. So, good. Include CS50.h. And now, anyone want to go for 4? No? All right, slightly unintended here. So let's see. Make buggy. Okay, no syntax errors, thanks to you all. So the code compiles, but of course, when I run buggy and I type in something like 3 manually, I'm still going to get 1, 2, 3, 4 out. So let me now introduce a more powerful tool that's generally known as a debugger. And within the VS Code environment that you're using, we actually have a command that makes it a little easier to use this tool, but we didn't write the tool itself. You are about to see a very graphical, a very popular industry standard tool called a debugger, but we'll start the debugger using a CS50 specific command called debug50, which just makes it easier with a single command to start the debugger without having to configure a text file with all of your preferred settings and all of that. It's just an annoying hoop otherwise to jump through. So what I'm going to do is go back to my code here. I have already compiled it, but just for good measure, I'll make buggy again because the debugger needs your code to be compiled. It's not going to help with syntax errors like the stupid mistakes I just made unintentionally. It will help you, though, with programmatic errors, logical errors in your code once your code is running. So to run debug50, I'm going to do this, debug50 space, and then the exact same command I would normally run to just run the program itself. So /buggy. So exact same thing, /buggy, but I prefix it now with debug50. When I hit enter, a whole bunch of another error is going to pop up on the screen, which is a good reminder because this will happen to you too invariably. It's reminding me that I have to set what's called a breakpoint. And as that word suggests, it is the point at which you want your code to break. Not break in the make the situation worse sense, but rather where do you want to pause execution, break execution, like hitting the brakes on a car. so the program doesn't run all at once. And you can put this any number of places, and you might have done this accidentally if you've ever hovered over the gutter of VS Code, the left-hand side next to your line numbers. See the little red dot that appears? If I click on any of these lines, that's going to set a breakpoint, so to speak. And I want to break execution at main, so I'm just going to click to the left of line 6 in this case. That makes it a darker red circle, a stop sign of sorts that tells the debugger to pause execution on that line, though I could put it elsewhere if I so choose. Let me go ahead and rerun debug50 /buggy, enter, and now a bunch of things are going to happen on the screen. It's going to look a little overwhelming perhaps at first glance, but there's some useful stuff that just happened. So one, my code is still here, but the line that I set the breakpoint on the first line of actual executable code at or below the breakpoint I set is highlighted in this yellowish green here, which says this line of code has not yet been executed. We broke at this point, but if I click a button, this line of code will be executed, right? Because up until now, every C program you write runs as fast as that. I want to pump the brakes and pause here. But notice a few other aspects of the window here. So notice that up here is some weirdness. There's mentions of variables, and we're familiar with these. Local is a term we'll use this week, but there's this variable h, which weirdly, where did the value 21,912 come from? So it turns out in C, before you initialize a variable with a value by literally typing the number 3, or by using a function like getInt, it often contains what's called a garbage value. More on those in a couple of weeks, but a garbage value is, you can think of it as like remnants of whatever was in the computer's memory before you ran your program. And that's a bit of an oversimplification, but you cannot trust that a variable will have a certain value in this case if you did not put one there yourself. So for now, H is sort of nonsensical. It's a garbage value, it means nothing, but once I execute this line, it should contain whatever the human types in. All right, down here, there's a watch section, which is a more sophisticated feature down here. Here's what's called the call stack, more on that in the future. But what this means for now is that I'm executing the main function, not, for instance, print column. So notice up here, these are the most useful controls within the interface. If I hit this play button, it's just going to actually run my program to the end of it without bothering me further. However, I can actually step over this line of code and execute it, or I can step into this line of code and actually poke around the contents of getInt if it's available on the system. So conceptually, you can either execute this line, or you can dive down conceptually deeper and see what's inside of that function. Lastly, this will let you step out. This will allow you to restart the whole process, and this will just stop the debugger. So these buttons are going to be our friends. And the one I'll click first is the first one I described, which is step over. So step over doesn't mean skip this step. It just means execute it, but don't bother me by going into the weeds of what is on this specific line, namely getInt. So when I click this button in a moment, you'll see that my terminal, which is still at the bottom, prompts me for a height. I'm going to go ahead and type 3. As soon as I hit enter, what part of the screen probably will change based on what I've said? So H, the variable H, should hopefully take on the number 3, and I'll probably see a different line of code highlighted, probably line 9 next, once I'm done executing line 8. So let me go ahead and hit enter and watch the top left of the screen. And voila, H now has the value 3, and execution has now paused on line 9, because the debugger is allowing me to step through my code line by line. Now let me go ahead and print out, let me go ahead and just say, all right, I'm done with this. Let's go ahead and run the rest of the program. It clearly got the value 3, but wait a minute. Oh, and at this point, it closed the window in which I would have seen the output. I would have still seen 4 hashes. So let me actually do this again. Let me go back into debug50 by running the exact same command again. It's going to think for a moment. It's going to reconfigure the screen. I'm going to do the exact same thing. I'm going to step over this line, but I'd like to actually see what's going on inside of my print column function. So this time, instead of just saying run to the end and close all the windows on me, let me go ahead and step into my print column function. Don't step over, step into. Because if I step over, and now this is what I meant to show earlier, you can see that it's still printing out 4. So in fact, let me undo this. Let me just stop the whole thing. Let me rerun the command a final time. So it goes back to where we began before. It's going to prompt me again once I step over line 8 for a number like 3, but this time instead of over line 9, I wrote print column, so let's look at print column step by step. Step into it and watch what happens to the yellow highlight. It now jumps logically to the inside of print column, thereby letting me walk through this code. And now I can just step over each of these lines one at a time. So stepping over, okay, so what did it do? It did that whole narrative that I did verbally last week where it compared I against height. It then went inside of the loop. When I step over, watch what happens in my terminal. 1 hash prints out. Now line 14 is highlighted again. It's comparing per the Boolean expression, I, is it less than or equal to height? If so, it's going to go ahead and print out the hash. It's going to do this again, print out the hash. But notice at the top left of the screen, height is still the same. It's still 3. But what has been changing apparently? I on each iteration. So the debugger is letting me see what's going on slowly inside of this loop because I keeps getting incremented. So if I step over this line now, notice that I've now printed 3. So ideally I want this loop to end, but if I click step over once more, notice that the value of I at top left is 3, but 3 is less than or equal to height. Oh, now I get it. If I play along here, now I see why less than or equals to mathematically is clearly incorrect. And as soon as that light bulb goes off, you can just sort of bail out, click the red stop button to turn the debugger off, go back in, fix your code, and voila, recompile, run it, and you're back in business. So the takeaways here really are just what tools now exist. Printf is your friend, but only for quick and dirty sort of debugging techniques. Get into the habit now of using debug 50 and in turn VS Code's debugger. You will invariably not take this advice, say for problem set 2 as you first begin, because you know it's going to feel easier and quicker just to use printf, just to use printf, just to use printf. And the problem with that logic is that you begin to build up like technical debt, so to speak, where you really should have learned it earlier. You really should have learned it earlier. You really should have learned it earlier, at which point you end up spending more time wasted using printf and doing things manually than if you would just spend 10 minutes, 30 minutes just learning the user interface and the buttons of a proper debugger. So please take that advice because it will save you significant amounts of time over time. Questions on printf or debugging in this way? Any questions on this? No? Okay, so let me give you a third and final technique for debugging, which has kind of been looming over us here for some time. So there is actually this technique known as rubber duck debugging. And in the absence of a roommate who's taking CS50 or who has taken CS50 or knows how to program, in the absence of having a TF or TA or CA sitting next to you, in the absence of having a family member available to ask questions of, if you have simply an inanimate object on your desk, goes the tradition, just talk to that inanimate object. Better yet, if it's an adorable rubber duck in this way. And the idea of rubber duck debugging is that simply by verbalizing, literally out loud, to this inanimate object, probably with the door closed and no one knowing that you're talking to this rubber duck, you invariably end up hearing any illogic in your own thoughts, at which point the proverbial light bulb tends to go off and you're like, oh, I'm an idiot. It's supposed to be less than, not less than or equal to. So literally just explaining to a duck or any inanimate object what's going on in your code will quite frequently just help you see in your mind's eye what it is you've been doing wrong. So rubber duck debugging is indeed a very effective technique, even if you don't happen to have a small or large rubber duck. Of course, you're also welcome to use the CS50 duck, who lives at CS50.ai and in VS Code at CS50.dev. You can ask the CS50 duck about concepts you don't understand, or you can even copy paste certain lines of code with which you might be having trouble and ask the duck for its own advice. All right, so with those tools in our toolkit, let me propose now that we introduce now a few lower level features of C itself and better understand how we can start solving some of those problems like the readability of text or the encryption of data. These were our so-called types last week when we introduced at least a subset of them or used them just to store data in a certain format, so to speak. Like in week 0, we said that everything at the end of the day is just zeros and ones, binary. And I claimed sort of conceptually that how a computer knows if a set of bits is a number versus a letter versus a color or a sound or an image or a video. It's just context dependent. Like you are using Photoshop or using Microsoft Word or something else. But last week, we saw a little more precisely that it's not quite as broad strokes as that. It's more about what the programmer has told the software is being stored in a given variable. Is it an integer? Is it a char, a character? Is it a whole string? Is it a longer integer? Or the like. So you now have this control. The catch, though, recall, though, is that each of these types has only finite amount of space allocated to it. So for instance, an integer is typically 4 bytes, and 4 bytes is 32 bits, because it's 8 times 4. 32 bits, we claimed, is roughly 4 billion, but if you want to represent negative and positive numbers, the biggest integer you can store is like 2 billion. Now that's really big for a lot of applications, but years ago, Facebook, for instance, was rumored to be using integers when they had fewer users, but now that they have billions of users, 3+ billion users, an integer is no longer big enough for the Facebooks, the Googles,
Yes.
the Microsofts, and so forth of the world. So we also have longs, which use twice as many bytes, but exponentially bigger range of values. Meanwhile, a bool,
Twice as
interestingly,
many.
is a byte, which is kind
Wow,
of
that
bad
was a dick
design in
move.
what sense? Why might that be bad design? It should only be 1 bit rather, because a 0 or 1 should suffice. Turns out it's just easier to use a whole byte, even though we're wasting 7 of those bits.
We don't
but
care about
bools
memory.
are represented.
Memory, we know.
And I'll write up a new program called.
Only one. Okay. Do.